All right, for this worksheet, we're just going to practice kind of what we've been working on with logarithms for the last couple of days. So this says find the domain for each log function. Use interval notation. You might need a number line. So remember the rule in general, whether it's log base A or ln x, you have the log of something. The domain is setting the parentheses greater than 0 and solve. So for the first one, x plus 2 needs to remain greater than 0, x greater than negative 2. So the domain for this one is negative 2 to infinity. For number 2, 3 minus x greater than 0. So negative x greater than negative 3. Divide by a negative. So remember, you've got to flip the symbol around. X is less than positive 3. Oops. So, sorry. Interval notation. So interval notation is negative infinity to positive 3. For the next one, x squared minus 4 needs to stay greater than 0. So this one is not just a little linear expression. So remember, you need to put, anytime I put a star next to it, it means we need a number line. You need to find the values for x. So x equals plus or minus 2, and then put those on a number line. This is just x squared minus 4, so we don't really have to test numbers in here. We can just say that's a parabola that opens up. So I know that x squared minus 4 is positive on the outsides and negative in between negative 2 and 2. So the domain are these outside sections. Anything from negative infinity to negative 2 will keep this expression positive, and anything from positive 2 to infinity will keep this expression positive. So those are the values in that logarithm. All right, for the next one, all right, this expression needs to stay greater than 0. So let's just, let me just go ahead and set that up. So all of these should be greater than 0 for every single one of these domains, okay? And then we're thinking about our rules here. So this is back to polynomials. So go ahead and start factoring it. You can take an x squared out of the first two terms. You can take a minus 4 out of the last two terms. Temporarily equal to 0 to get our number line values. Now there's a GCF of x minus 2, which would group together x squared minus 4. Now this can be factored a little bit further. And because we're going to be graphing this polynomial, you do want to combine multiplicities, like x minus 2 is actually squared times x plus 2. That matters if you're going to be graphing this little graphing this polynomial rather than just testing numbers into it. So I get x is negative 2 or positive 2. The end behavior of this x cubed graph is up on the right, down on the left. The graph should be not changing signs at positive 2, and it should be changing signs at negative 2. So informally, bouncing at 2, crossing at negative 2. So like this. That means it's negative, positive, positive. So we want the positive sections. Remember, we can't equal 0, so leave out these two values. So it's going to be anything between negative 2 and 2, and then anything from 2 to infinity. It's not just negative 2 to infinity. You've got to leave the positive 2 out as well. For this one, x plus 1 over x minus 3 remains greater than 0. Remember how, I should be putting stars next to all of these, shouldn't I? Remember how rational inequalities worked. This is just our previous chapter 2. You're not allowed to multiply x minus 3 over. You get your critical numbers by finding the x-intercept and the vertical asymptote. X-intercept is negative 1. Vertical asymptote is 3. You put those on a number line. Both of these will be open circles because just greater than 0 and vertical asymptote. This one we should go ahead and test into the value. So if I test negative 2 into this, I get negative 1 over negative 5. That's positive. If I plug in 0, I get 1 over negative 3. That's negative. If I plug in 4, I get 5 over 1, positive. Again, we want positive sections. So this domain is negative infinity to negative 1 and 3 to infinity. Really, this is all chapter 2 stuff, right? We're going back to these inequalities. The only thing that makes it into chapter 3 is that we're starting with a log function. So the only thing that makes this chapter 3 is that you've got to know, okay, I'm supposed to set this thing, this expression in the log greater than 0, because we can only log and natural log positive values. I can subtract 4. I divide by negative 2, which means I need to flip the symbol around, so x is now less than positive 2. No number line needed if the little expression is just a linear expression. But if it is quadratic, if it's higher degree polynomial, if it's rational, I should be using a number line for those. Okay, so that's the first thing. True or false? If it's false, expand or condense the right side of the equation to make it true. So let's see. Is the natural log of 4x equal to ln 4 times ln x? This is false, right? So what does it mean by expand or condense the right side? So first let me answer this. False. Because what is ln of 4x? It shouldn't be ln 4 times ln x. It should be ln 4 plus ln x. So this is what it should be, but that's not what it said. Okay, what about this next one? So is this true or false? So natural log of square root of x, y, z. So what we're really doing is testing your expanding and condensing skills. So what did this over 2 come from? Now remember, dividing something by 2 is the same as having let me put it here, same as having a 1/2 out in front. If you looked at it like this, would you say true or false? Hopefully we would say true, because the 1/2 is coming from the square root. All of those have a 1/2 out in front. And then because we're multiplying x, y, and z, we should be adding ln x plus ln y plus ln z. And yeah, that's the same thing. So this is true. I'm going to write should be right here. Okay, this one's true. And then the last one, let's see. So log base 3 of x over y, does that turn out to be log base 3 of x divided by log base 3 of y? Think about your expansion rules. We have 3 ways to expand logs. We can add them, we can subtract them, or we can pull numbers out in front. There's absolutely nothing about division unless it's like a change of base, which this is not. So that's false. What should it be? So let me write should be. If I have log base 3 of x divided by y and I tell you to expand that, it should be log base 3 of x minus log base 3 of y. Okay. Evaluate and simplify. For the problem that I have 2 little stars next to, try the change of base formula. We'll talk about that in a minute, or I'll remind you what that is in a minute, I should say. And then 1 star is condense first. So these are evaluate problems. So let's see. Natural log of 1. Remember, evaluate means determine the exponent in most of these cases, or sometimes it means use a property. So natural log of 1 we should know is 0, and that's because e to the 0 equals 1. This is the same as natural log of e to the negative 1, so the answer is negative 1. You don't have to rewrite this for me, but again, you're just trying to say, what is the exponent on base e here? So this one is negative 1/2, because this is the same as natural log of e to the negative 1/2. What about this one? What are we going to raise 3 to get 1 over 27? Right? So that's got to be negative 3. The negative takes the whole number to a fraction, and 27 is 3 to the third. For this one, natural log of 1 is 0, plus natural log of e to the 4th is 4. 0 plus 4 is 4. Remember, if a base number is not showing, then it's base 10. And don't overthink these, just count the zeros. This is 10 to the third, so the log base 10 of 10 to the third is 3. The log base 10 of 10 to the 6th is 6. 3 plus 6 is 9. 64 to what power equals 8? What's the relationship here? If I square root 64, oops, not square root both sides. If I square root 64, I get 8. So it's 64 to the 1/2 power equals 8. So this answer is 1/2. Anytime you go from a whole number to a smaller whole number, it's going to be some sort of root. Is it a square root, a cube root? That's what you're trying to figure out. Okay, we've got properties in these terms. E to the natural log of 8 cancels out to 8. E to the natural log of 2 cancels out to 2. Minus the natural log of e, that's minus 1, right? Because this is saying e to the what equals e to the first. The answer is 1. 8 plus 2 is 10. Minus 1 is 9. 18 is the same as 10. I did that on purpose because this pops up a lot. Natural log of 1 just pops up a lot in this class and next year. And in BC Calc, we're in this chapter now. We see natural log of 1 a lot to simplify. So you've got to know that one. What about these? Notice I'm not condensing any of these that I can just simplify individual terms. So this is the same when it's cube root of e squared. That's the same as e to the 2/3. So that answers 2/3 plus 1/2. I do need to get a common denominator here. So 4/6 plus 3/6 is 7/6. 3 to what power is 81? Now, if you don't know this off the top of your head, go with one you know. Like maybe you know 3 to the 3rd is 27. And so you just say, okay, I don't know, do I just multiply by one more 3? And then hopefully you figure out that yes, you do. That's 3 to the 4th, right? If 81 is 27 times 3, that's 3 to the 3rd times 3. So this is 4. Sometimes you just have to do the multiplication. It's not going to be 3 to the 11th power or something like that. It's only going to be 2, 3, 4, stuff like that. 5 maybe. Okay, for the next one, this is just a property. The 3 to the log base 3 of 10 is just 10. Okay, now what about this one? Because you can't say 3 to what power is 8. That's not a nice number that we can do without a calculator. And same thing here. So that's where my stars come back into play. Try the change of base formula. So what was the change of base formula? Let me just review that with you from our notes. It was the log, I can't remember how I wrote this exactly. The log base a of x is equal to, you can either make it log base 10 of x divided by log base 10 of a, or you can make it ln x over ln a. It does not matter, and it doesn't matter in this case either. So I'm going to switch it to ln's, I think. So this can be, well, no, sorry. I'm going to switch it to logs. It literally does not matter, but I think people will like it better if they're logs. So, okay. So log base 3 of 8 can be log of 8 divided by log of 3. Okay. And log base 8 of 81 can be log of 81 divided by log of 8. So the reason change of base formula is where we want to start is because now these are two rational expressions being multiplied, and the log base 8s can cancel. So now it's log of 81 over log of 3. Now, reverse change of base. So because we're not finished yet, this can be simplified further. This can be, go backwards. You have log of something over log of something. Go back to this. So this is the log of the base numbers down here of the result, which is 81. 3 to what power is 81? We just did that one previously. That answer is 4. So when I'm giving you these problems, I am setting them up to simplify down to a single number. So if you don't get it down to a single number, you want to keep going. Okay, for number 23, there's a little star next to this one. That's because 2 to what power is 100? That's not a nice answer. 2 to what power is 25? Not a nice answer. So let's try condensing this first. So let's condense it to the log base 2 of 100 divided by 25. That's pretty nice because that's just the log base 2 of 4. And that's easy. 2 to what power is 4? 2. 5 to what power equals negative 125? It's not 3. That would be positive 125. It's not negative 3. That would be 1 over 125. It's not 1/3. That would be the cube root of 5. This is no solution because there's no exponent you can raise a non-negative number to and have it come out negative. That's not how exponents work. You'd have to multiply by a negative for that to happen. So negative 125, not in domain. Remember, we can only log something greater than 0. What about this one? Am I really going to figure out 64 to the 5th? Absolutely not. I don't want you to do that. But remember, you can work on your expanding rules here. So let's get this exponent out of here by putting it out in front. This is 5 times the log base 4 of 64. The log base 4 of 64 is a number I know. That's 4 to the 3rd is 64. So this is really just 5 times 3. The log base 4 of 64 was 3. And 5 times 3 is 15. Okay, now be careful on number 26. The star is here again. And what did the star mean? Condense first. And I'll show you why in a minute. So condense in here first. This is e to the natural log of 6 times 7 is 42. Now you can cancel out and get 42. Here's the most common mistake. So this is wrong, but I want to show it to you anyway. It's wrong to say cancel 6 plus 7, 13. That doesn't work. It's not the same answer. It's not the same as 42. So in order to use this property, this canceling e to the ln, it has to be a single term. You can't have any addition in your exponent for that to work. Okay, 27, back to doing change of base again, because log base 10 of 27, log base 10 of 3 is nothing. But this is just log base 3 of 27. So you're not allowed to can't cancel logs. Like you can't say, let me do this. You can't say, boom, boom, 27 over 3 is 9. Can't do that. This is illegal math. But instead you're saying 3 to what power is 27? 3 to the 3rd is 27. Log base anything of 1 is 0 because 8 to the 0 is 1 in this case. Can I raise 2 to a power and get 0? No. Remember our domain for logarithms? The thing inside the logarithm has to be greater than 0. So this is no solution. This is 4 to the log base 4 of 75. There's no extra addition or subtraction going on, so I am allowed to cancel those, and I get 75. And this one too, again, you can't cancel ln's, but you can change of base. You can say this is the same as the log base 5 of 25, and that's just equal to 2. It can get confusing, I know, because we are not used to working with logarithms. We have not been working with logarithms for as many years as we've been solving algebraic equations. So it's understandable if you want to do some of these algebraic things like canceling, but you just can't do it. So try to write down these little rules as you're checking your answers as well. Okay, last few problems here. A is equal to the log base A of 2. B is log base A of 3. C is log base A of 5. Rewrite each logarithm in terms of A, B, and C. So it should be expand first. And then it should be sub in A's, B's, C's. So let's expand to this first. So this is equal to the log base A of 30 minus the log base A of A. 30, I need to break it down into 2's, 3's, and 5's. So let's think about factoring 30. It's log base A of, so 30 is what? 10 times 3 or 2 times 3 times 5. It doesn't matter what order you write that in. What about log base A of A? A to what power is A? 1. So that log goes away. I can simplify that to 1. Now expand this again. Log base A of 2 plus log base A of 3 plus log base A of 5 minus 1. Now sub in the letters. A plus B plus C minus 1. If you wrote your 2, 3, and 5 in a different order, it doesn't matter. You should have the sum of A, B, and C in any order and then a minus 1 on the end. Same thing here. Expand first. Log base A of 32 plus log base A of A squared. 32 needs to get broken into 2s, 3s, and 5s. So 32 is what? Excuse me. It's 2 to the 5th, right? So this is log base A of 2 to the 5th plus, what's log base A of A squared? 2. Now this is not just 5 because it's base A and this is base 2. So again, I simplified this one to get 2. And then here, what's the expansion rule here? Pull the exponent out in front. 5 times log base A of 2 plus 2, which is 5 times, what is log base A of 2? That's A plus 2. So you're not always going to have A, B, and C, all 3 letters in here. This is not the same as A to the 5th. It has to be 5 times the log. So expand, how about this? Expand, rewrite in 2s, 3s, 5s. Then sub in, then maybe expand again. And then the final step is sub in letters. Okay, for this one, I'm going to do expand first. So log base A of square root of A minus log base A of 40. The log base A of square root of A is 1/2. Minus log base A of 40 is 8 times 5. So 8 times 5 is 2 to the 3rd times 5. I better erase this for my key there. Okay, so let's expand that. 1/2 minus log base A of 2 to the 3rd minus log, because it's plus, but I'm distributing the minus through. How about we do it like this? Minus the quantity. So plus for the multiplication. Log base A of 5. Expand a little bit more. Remember, you're not finished if you have exponents left. And let's distribute our negative. So minus 3 log base A of 2 minus log base A of 5. So this is 1/2 minus 3A minus C. Okay, last one of these. Log base A of 25 minus log base A of 6. Log base A of 5 squared minus log base A of 2 times 3. 2 times log base A of 5 minus parentheses log base A of 2 plus log base A of 3. I'm going to distribute the negative and I'm going to fill in my letters. So 2 times C minus A minus B. All right, last 3, let's graph these. So, all right, what are the nice points on the log base 2 of x graph? We have 1, 0, and we have 2, 1. There's a vertical asymptote normally at x equals 1. So the domain, well, we'll do all this stuff in a minute. Okay, so we're going to go right 4 and up 1. So take the point 1, 0, go 1, 2, 3, 4, and up 1. 2, 1 goes 1, 2, 3, 4, and up 1. The vertical asymptote that was at 0 is now at x equals 4. And I don't have a nice x-intercept, so I will have to solve for that. What's the domain? The domain is 4 to infinity. Either get that by solving or just look at your graph. The range is all reals for every log function. The asymptote is x equals 4. And then, yeah, how do we find this x-intercept if it's not a nice point on my graph? So the x-intercept is when y is 0 You're setting log base 2 of x minus 4 equal to 0, plus 1 equal to 0. Get the log by itself. Negative 1 equals log base 2 of x minus 4. Now rewrite in exponential form. This becomes 2 to the negative 1 equals x minus 4. 2 to the negative 1 is 1/2. Add 4, x equals 4.5, which kind of looks right on my graph, right? Okay, this one, the nice points, because it's base 5, are 1, 0, and 5, 1. We're going to go left 2, down 1. So 1, 0 goes left 2, down 1. 5, 1 goes left 2, down 1. The x-intercept, or I'm sorry, the vertical asymptote is at x equals negative 2 because we went left 2. So let's graph this. The domain is negative 2 to infinity. The range is always all reals. Vertical asymptote x equals negative 2. I don't need to solve algebraically for the x-intercept. I can just see on my graph that it's 3, 0. For this one, the nice points originally are 1, 0, and 4, 1 because it's base 4. The 2 on the inside means the x's will get divided by 2. And the negative on the outside means the y's will get multiplied by negative 1. So let's do that. This becomes 1/2 0, and this becomes 2, negative 1. No shifting, so let's just plot those points. 1/2 0 and 2, negative 1. Vertical asymptote would still be at 0. And the graph should be looking like this because it was an x-axis reflection. So domain is 0 to infinity. Range is still all reals. Vertical asymptote x equals 0. And again, I already have the x-intercept. It's at 1/2 0. Okay, that finishes this worksheet. That kind of practices a pretty difficult version of everything we've looked at with logarithms so far.